the participants that after the talk there will be a question and answer session. You may enter your queries in that chat box also. We are just few seconds away from the beginning of very informative international webinar series, part 3. We are live on Facebook and YouTube. You can join there also. So some participants have still not joined, so we are just waiting for them.
Dr. Ritu, your voice is very feeble.
Pardon, sir?
सर को आपकी आवाज थोड़ी कम सुनाई दे रही है, बट as far as I'm concerned मुझे तो ठीक आ रही है. What about rest of you?
Okay, ma'am, I am putting one earphone. Right?
अब थोड़ा डिस्टर्बेंस आने लगी तुम्हारी आवाज में.
Am I audible now? Good morning, everyone. Am I audible now?
Yes, Ritu.
Okay, fine. Okay, fine.
काफी कम है वॉल्यूम.
वॉल्यूम कम है थोड़ा.
Good morning. Is it fine, sir? Now the voices. Good morning, everyone.
Yeah, this is better.
Yeah, now it's okay.
Okay, fine, sir.
Good morning, sir. Is it good to start now, Director sir? Director sir is mute.
Please go ahead, Dr. Punam.
We'll start the program now, sir.
Yes, please go ahead. Good day.
Okay, sir. Thank you. Ritu, good to go ahead. Start.
Jai Hind, ladies and gentlemen. Science is not meant to cure us of mystery, but to reinvent and reinvigorate it. Science impacts many aspects of our lives. Simply put, without it, we would not be enjoying many of the things that make our modern world possible.
Your
From the
voice
houses
is
that
very
we live in,
feeble. Voice is
food
very
that we
feeble.
eat,
रितु मैम ईयरफोन निकाल लीजिए आप.
Increase your volume.
Now try.
Shall I begin again?
Yeah.
Yeah.
Okay, Jai Hind, ladies and gentlemen. Science is not meant to cure us of mystery, but to reinvent and reinvigorate it. Science impacts many aspects of our lives. Simply put, without it, we would not be enjoying many of the things that make our modern world possible. From the houses that we live in, the food that we eat, the car that we drive, to favorite electronic gadgets and technologies. It has going make our lives easier. With these lines, I, Dr. Ritu Sharma, welcome all the participants to the third talk of International Webinar Series organized by the Department of Applied Science and Humanities, RKGIT, Ghaziabad. It's our pleasure that we have participants from all over the world. We feel honored to welcome Professor Anurag Sharma, the speaker to illuminate about Photonics Revolution, the topic of today's talk of International Webinar Series. Now, I request Dr. D.R. Somashekar, Director RKGIT, to deliver welcome address.
Thank you, Dr. Ritu. Am I
Welcome,
audible?
sir.
Am I audible?
Yes sir, you are audible.
Yes, sir. You are audible.
Thank you very much. Good morning, ladies and gentlemen. Honorable Speaker of the Day, Professor Anurag Sharma ji, Department of Physics, IIT Delhi, respected Group Director Dr. Lakshman Prasad, Convener of the International Webinar Series Dr. Poonam C. Kumar, HOD of the Applied Science Department, coordinators Dr. Sanjeev Goyal and Dr. Pavan Sharma, delegates from India and abroad, invited guests, respected participants from different institutions affiliated to the AKTU and other universities, committed band of teachers, and my dear friends. I deem this as my proud and privilege to welcome you all on the third talk series of the International Webinar Series organized by the Applied Science Department of Rajkumar Goyal Institute of Technology, Ghaziabad. Friends, at the outset, let me take this opportunity to welcome our Honorable Speaker of the Day, Professor Anurag Sharma. Sir, in spite of the pandemic COVID-19, you made it convenient to be with us, connected on the virtual platform, and for gracing the occasion. Sir, we are highly grateful to you, and on behalf of the management, on behalf of the committed band of teachers, and on my own behalf, wholeheartedly welcome you, sir. also take this opportunity to extend a hearty welcome to our Group Director, Dr. Lakshman Prasad. On behalf of the committed band of teachers and on my own behalf, I welcome you, sir. I also extend a hearty welcome to all the invited guests, participants from India and abroad. I also take this opportunity to welcome the complete parivar of the RKGIT, Ghaziabad. Friends, you know today's topic is Photonics revolution. We are highly honored to have a very renowned person in this field, Professor Anurag Sharma. Friends, I don't want to be in between the speaker of the day and you. Only thing is I can wish the success of the program and also for the future coming webinar talk series. Thank you very much, and once again wish you good luck. Over to Dr. Ritu.
Thank you, sir. I feel honored to get this opportunity to introduce our speaker, Professor Anurag Sharma, for today's talk. Professor Anurag Sharma, a JC Bose Fellow, is a class of 66th-year Professor of Physics at IIT Delhi and has been teaching since 1980. His research has been concerned with propagation of light in imaging and wave guiding devices. He has published about 100 journal papers. He received the Shanti Swarup Bhatnagar Prize in 1998 for his research contributions. He is a fellow of all the 3 Indian science academies in India, INSA, IAS, and NASI, the Indian National Academy of Engineers, which is called INAE in short, and of the OSA, the Optical Society USA. He is currently the President of Optical Society of India. Welcome you, sir. I invite Professor Anurag Sharma to share his knowledge with the participants. Now, without further ado, we will turn the time over to Professor Anurag Sharma, Speaker of the Day.
Thank you, Ritu. Thank you. I would like to thank the organizers, the Rajkumar Goyal Institute of Technology, Management and Leadership, for giving me this opportunity to speak to national and international community on a topic which I work on, and I'll give a general talk, of course, not a very specific depth of the equations that I usually solve. But what I'm going to talk about is the photonics revolution that is going on and how India can play some role in it. So let me share the slides. Can you see the slides now?
Yes, sir.
Yes, it can be seen.
Okay,
It's very
fine.
clear.
Good. Yeah, right. So what I'm going to talk about, as I said, how photonics is helping the society, at least some aspects of it. It is helping in many, many ways, but some aspects which are close to my understanding and my work, I'll talk about that and see what we should do. So as you all know, this talk is online. Some of you are using laptops or desktops, but most of you, I guess, are using mobile phones, particularly the young students who are sitting at home may not have access to desktops or laptops. So mobile is the device which is most commonly used these days. A mobile today is used more for data than for talking. In fact, we used to call it mobile phone. Now the phone is dropped. It's just called mobile, right? So and the most popular apps that you see are listed here: WhatsApp, Messenger, Facebook, etc., etc. Large number of them. But that was the scene before the COVID started. With the onset of the COVID-19, other apps like Zoom, on which we are right now connected, MS Teams, Google Meet, WebEx, etc. have gained popularity because most of the classes, educational activities, seminars, everything is now happening on this. In fact, most of the you know jobs these days are work from home, and they all require this kind of connectivity. So life without a mobile is difficult, to say the least. And but more correctly, it's life without an internet is difficult. So whenever we go to a new place, whether a hotel, I mean, at least till 4 months back, we used to go to some hotels, travel, and so on. First thing we will say, where is the connectivity? Which place is the connectivity the best? What is the password, etc., etc. Because without an internet today, to think of life is become really very, very difficult. So what is the, because the backbone of all this is the internet, whether the mobile or social media or whatever you want to, laptop, you want to see emails and so on. So in the world of internet, if you see, the social media is, just a minute, yeah, okay, yeah. Social media, low cost telephone calls, video conferencing, which we are now doing with family and friends, and now with school, between teachers and students, are three examples of how internet allows people around the world to feel connected in a way that has never before been possible in the history. And I'm not showing this particular last line, which I'll show a little later. This is this was said by the UNESCO committee, which looked at the various activities. The internet is actually now threatening the governance all over the world, actually. So in 2016, this is a web page from the Council of Europe, which formed a committee to see how internet and the governance will go together, and how they can sort of look at the use of internet and how it will sort of kind of penetrate, whether they will be able to control it, not control it, and so on. So this is something which is happening. Closer home at in India, the Supreme Court declared on January 2020 that access to internet is a fundamental right. Now, this is something very, very unique, because any technology being a fundamental right probably is the first example in the world. And this was internet was declared as fundamental right by the Supreme Court in a particular decision connected with the freedom of expression. Another example is, this is an interview in the beginning of the year. This is one Mr. Richard Sharma, who gives sort of advice, or let's say predictions for the coming year, or in fact he was doing for the coming decade when he was doing this year. And he said that the top 10 trends, one of the top trends will be the rise of the fifth state. And what is the fifth state? You know the four states: judiciary, legislature, and executive, and the fourth state is called the press. Now, this is the fifth state, they say, is the online media. And they say the rise of this fifth state will be a major trend in the next decade, because this will penetrate, because it knows no boundaries. All the governments are now trying to see how we can control the flow of internet and flow of information in the internet. So it has become really something central, not only to the society, but also to the governance. If you look at the world of internet, this is January 2019, 67% population was using mobile. 57% people had internet access. And this is a very large number. This is a very huge population. In India, the internet users are around 40%. So this internet revolution that is taking place has at the core is the optical fiber. The lifeline of the internet is the optical fiber. If you look at the on the right panel here, this is a fiber cable in which these are fibers. This is a strength member. These are fibers. In one cable, you may have multiple fibers. And these are the typical connections that you have optical. This is optical line connections within the computer board and so on. This is typical connection jack. So the lifeline of the internet is optical fiber, and what gives life to this line is the light. So really light is the life of all this. And that's the point I was trying to make here when this UNESCO committee said that all that is happening is all of this technology is because of light. So what is light? Light has this kind of parameter, and light is the subject which is being taught in the form of optics, which is the science of light. But then the photonics is a new word, which is science and technology of light. And photonics revolution is something that we are witnessing today because of various applications in the society, the way society being changed because of light. So light has fascinated mankind ever since the man could observe. Of course, from the very beginning, we had eyes and we could see around, and this was fascinating. The mechanism of seeing, how do we see, was under study since the time of early philosopher, whether Greek or Indian or any other. In the last 4 centuries, major strides have been made in the understanding of light and its uses. Particularly, we all start with Newton, although there were studies earlier also. But it was only about half a decade back, that means 5 years back, that the world got up and acknowledged the due importance of light in the way they declared in 2015 the International Year of Light and Light-Based Technologies. And also to perpetuate the celebration, International Day of Light is now celebrated every year on May 16th. And the importance of May 16th, I'll come to later. Probably most of you would know. So light and light-based technologies, on the most fundamental level, through photosynthesis, light is necessary to the existence of life itself on Earth. Everything comes from the sun. All the energy comes from sun in the form of light. And many applications of light have revolutionized society through medicine, communication, entertainment, and culture. All over the globe, people are using light to discover solutions for society's most pressing problems. In fact, most of the engineering now, light is entering in most of the engineering fields in some way or the other. And that is why I always say it's important for our engineers when we train them to know a little bit of about light, what light properties are, so that if there's a problem, they can actually use light to solve that problem. From 3D printing to bringing energy solutions to developing regions, light is the key in driving economies and encouraging the development of civilization. So if you look at the photonics economy, which is the light and light-based technologies based economy, business in the field of photonics and light-based technologies work on solving key societal problems, challenges such as energy generation, energy efficiency, healthy aging of population, climate change, and security. And what is expected is that in the next 5 years, it will grow, the photonics market in the world will grow at the rate of nearly 8%. Of course, this was before COVID happened, so things must have changed, but this is what was expected. If you look at the photonics market, India is on the high growth trajectory. If you look at this, the green colored sections are the ones where it is expected that the growth would be very high of photonics and photonics market. This is basically concerned with market. And technology, the key areas are listed below: surveying, detection, data communication, medical technology, production technology, image capture and display, lighting, and many other areas. However, if you really look at in detail, because this green involves China and India both, but what is expected is that China will be the world's factory in photonics, whereas India will be the market. Not a very happy situation. We should also be at least part of the factory. But anyway, that is how things are projected internationally at the moment. So coming back to the science of optics, the Nobel Prizes, which are the highest recognition of any scientific discovery or invention, there have been 18 Nobel Prizes in physics given to 30 scientists, 1 in chemistry and 1 in medicine, which were related to optics. In 2014, both physics and chemistry Nobel Prizes went to optics related subjects. Last year, last year, 2018, the Nobel Prize was given to laser applications. So light at work, it has been at work all the time, although the world has now got up and recognized. So I'll give you a few examples here. For example, optical instruments aided astronomy to grow. Because if there were no telescopes, there will be no astronomy or astrophysics. You cannot see the heavens. You cannot see the sky. Microscopes, microscope is an optical instrument. Without microscope, you cannot think of biological investigations or medical science growth. And even today, in 2014, the Nobel Prize in Chemistry was given to a microscope, the development of microscope. Similarly, any material science or chemistry cannot be done without spectroscopy. And spectroscope is an optical instrument. So there are three basic instruments which we never actually we talk about astrophysics and astronomy and medical sciences and so on. We don't even stop to think that silently under these are the optical instruments which are working. So optical technology has always been an enabling technology, and it continues to be so. So if you look at the entire gambit of optics, I will not go into the details of all this, but you can divide in two parts mainly. One is optical physics, as we call, which is basically more fundamental things. And then the second is optical engineering, where you actually develop instruments like telescopes, microscopes, spectroscopes, all will come under this category. Over the years, the revolution that is taking place today is built on the breakthroughs in optics over the years. We know most of the breakthroughs in optics. For example, Newton showed colors in white light. He also said how the light propagates. Light is a wave that came with Huygens and Young. Electromagnetic wave nature came with Maxwell and Hertz. Quantum nature came with Planck and Einstein. And then the lasers and masers came with Einstein, Towns, and Mem. But not much is known about the breakthroughs in engineering optics, because those are the things which actually build the things. One is the principles and fundamentals, the other is. So, for example, cameras came with Da Vinci and Galileo, telescope, microscope, Galileo, spectroscope with Wollaston, lens design with Wollaston, optical system theory with Abbe, camera with Daguerre, grating spectroscope with Fraunhofer, Michelson interferometer, Raman spectroscopy, FTIR spectroscopy, phase microscopy, holography, optical fiber, laser diode, blue LED, all these are engineering optics applications. And I'm sure not many of you are very well versed with these, but these are equally important and something that we should look at seriously. So I'll give you some examples. For example, imaging, because one of the first applications of optics was to aid the eye to see things better. Whether it was when eyesight becomes weak, then this monocles or spectacles, or whether you want to see things, very small things with a microscope, whether you want to see very far things with a telescope, these are all to aid the vision, aid the eye. And it was Galileo who, for the first time, did the serious study and made a telescope and a microscope, although they were there in some form earlier. And both these became, as I said, important tools in astronomy and biology. In early lenses, camera obscura or pinhole cameras, these were also there. But really development took place after the photography was invented, because then people wanted now a system which can actually create portraits or create landscape images. And that is how a large amount of developments took place in the 19th and 20th century, in which I'll just list some of them, like zoom lenses came up, molded lenses, aspheric lenses came up, diffractive lenses, gradient lens, freeform optics, adaptive optics is something very, very important these days. But most importantly, something which has come to very close to us is the camera and the mobile. And initially it was not a big thing, because it was just a question of miniaturizing the optics and using 3 or 4 optical elements inside the camera, because the thickness of the mobile phone is very, very small, and you wanted actually thinner and thinner. So the space was very limited. So a lot of innovation went into this. And in fact, now I don't know how many of you have seen, now you have mobiles with multiple cameras, 2 cameras, 3 cameras, 4 cameras. In fact, 16 camera lenses, mobile phones are sort of already patented, are going to come. So this is also a lot of innovations have gone into this, but that story some other time. That's a story itself. Spectroscopy developed over the years, since starting with Newton when he showed colors through a prism. Then Wollaston made a first spectrometer based on Newton's experiment. Then Fraunhofer came in to use gratings instead of prisms, and so on. And today, the spectroscopy is really very important for studying any material. The only way that you can know which material, what you have, is the spectroscopy, and also chemistry cannot survive without this. So scenario at the end of 19th century, when the electromagnetic theory of light was established, Maxwell's equations were well established and experimentally verified. Then the Michelson is supposed to have made a statement in 1894 that it seems probable that most of the grand underlying principles have been firmly established. And eminent physicists remarked that the future truth of physical science are to be looked in the 6th place of the decimals. What he meant was that everything is known. Only thing what is remaining is to measure things more and more accurately. And this was said in 1894, which was, as we say, he spoke too soon, because just at the turn of the century, we got the quantum mechanics or the quantum concept. And in optics, the establishment of light quantum photon, which was called later photon, was established through the work of Einstein on photoelectric effect and other works. Einstein also predicted in 1917 the mechanism of stimulated emission, which is the basis of lasers. Raman in 1928 discovered his effect, which opened an entirely new direction in spectroscopy. Holography was invented by Gavor in 1948 as a new kind of imaging process, and that has revolutionized many measurement processes. First measure was made in 1957. Measure is a microwave laser, and was first used, which used first the stimulated emission process. And soon after 3 years, the first laser, the ruby laser, was made by Mayman in 1960, heralding the beginning of the new era in the field of optics. And that was, he declared this on May 16th in 1960, and that is why May 16th is now sort of celebrated as the International Day of Light. So now we have 60 years of lasers, starting with 1960, and we are now 2020. So it's the 60 years of lasers. Lasers have ushered in a new phase of activities in optics, so much so that a new word, photonics, had to be coined to encompass all the activities in the area. Many other new activities started, and this optics was not just good enough. Also to convey the technological aspects, it was important to make something called photonics, which is in parallel to electronics. Last 60 years have seen innumerable innovations and developments in the field of optics and photonics. First 60 years, that means 1901 to 1960 till the lasers came in, only 4 Nobel Prizes can be counted as given to optics related work. While in the later 60 years, since the lasers came in, there were 11 Nobel Prizes in this 60 years, which is in fact 14 innovations and discoveries, because many times you get 1 Nobel Prize with two persons together. So 2015 was declared as Year of Light and so on, as I said, and May 16th is now celebrated. So what are the areas? What are the developments which were waiting for a source like laser? Holography and interferometry. It needed a source with large coherence length. Now, what does that mean? Coherence length is a is a property of light which enables interference to take place. If the coherent length is large, it's much easier to make a interference experiment. If it is small, then there's a problem. So with lathe and Optics, 1963 demonstration of off-axis holography. Holography in its application to various fields, including interferometry and non-destructive testing, led to the recognition of Gabor's work, which was done in 1948, and he was given the Nobel Prize in 1972. That happened only after people realized how important it was. The other area is nonlinear optics and spectroscopy, especially Raman spectroscopy. It needed a source with high intensity because it was basically scattering and nonlinear scattering. And scattering was very, very small. So you needed a very strong primary source to get measurable scattered light. So nonlinear optics, particularly with ultra-short laser pulses, broke new ground. This ultra-short laser pulses this technology was given Nobel Prize in 2018. And this has completely changed how the lasers can, or the light can interact with matter. And this has completely new kind of spectroscopy, new kind of interactions have come up. And this kind of thing work was recognized in 1981 with the Nobel Prize to Blumberger and Shallow. And then finally, a communication. It needed a source with high directionality and intensity. And that's precisely the laser was. So dream of communication engineers of using optical frequencies for communication to gain an advantage of 1 million in capacity became a reality with lasers. Optical communication have played an important role in the spread of knowledge economy of today and in the way societies connect and communicate, as I have said earlier. Its wide-ranging impact was recognized by Nobel Prize in 2009 to C.K. Kao for a seminal work done in 1965. Although light was used for communication earlier with fire and flag signals and photophone of Bell, but those were all experiments and very limited value. What are the other developments which have taken place with lasers? Broadly, some of the application manufacturing, including additive, like 3D printing. Military is using lasers, these are in a big way for target detection, ranging, guidance, and annihilation. So lasers not only can image and see where the enemy installations are, they can actually find the distance and destroy them just by laser. So laser is being used. Medicine, including surgery, therapy, and imaging. The optics and photonics is in a great demand. Information storage and transmission, I'll talk about this a little more. Entertainment, displays, and shows, you have seen those, the so-called holographic images. Those are not really holographic, but they are laser displays in some sense. They're not strictly holographic. Construction and surveying and ranging. These days, nobody takes a tape and measure the distance. You just have a laser gun kind of a thing. You shoot and you get the distance. Leveling is also very easy. Light, decorative lighting, stage illumination. In fact, not really laser, but if you see photonics, LEDs have revolutionized completely the way you light your spaces, whether in interior or exterior or anywhere. And the power consumption has gone down, and the kind of possibilities in decorative lighting that you have with LEDs is innumerable. I mean, it's unbounded. People are coming with new kind of designs. So let me just focus on communication a bit, because that's the subject that I work in. So development in communication, if you see, in 1834, we had Morse telegraphy. Telegraphy is now officially dead the world over, but till about 25, 30 years back, telegram was still being used. Telegraphy was something like Twitter today you have, where limited words and can be sent quickly and so on. 1874, we had Bell telephone. 1900, we had Marconi and J.C. Bose radio waves. In 1940, we had microwave communication during the World War II. But it was known since the radio communications that as the frequency of the carrier wave goes up, the signal carrying capacity also increases. So that is why people moved from radio waves, which are frequency was in kilohertz or megahertz, 2 microwaves, which was in gigahertz. Gigahertz is 10 to the power 9. That was the microwave communication. But optical wave is 10 to the power 15. So it's a 10 to the power 6 times more frequency. And that means 10 to the power 6 times more information can be sent. So that's a huge advantage. And that is what people have been looking at. But optical communication became possible because of laser. With normal light, it was not possible because normal light is any bulb will give light in all directions and you can't have a very intense beam going in a particular direction. Very small light would be remaining. So you needed a laser. And as soon as laser came in 1960, the communication engineers started thinking about how to use that source for communication. But unfortunately, as the frequency goes up, the wavelength goes down. That's the fact of life because velocity is constant. And hence, where microwave had the wavelength which was in centimeters and millimeters, with optical waves, the wavelength became in microns, or half a micron, about a micron. And with this small wavelength, the effect was that they can be scattered very easily with dust particles or fog or any cloud or whatever. And hence, this light cannot be used like in the case of microwave through open air channels. So there was a need for a channel which was guiding, which was secure, which will keep this light away from all these vagaries of the atmosphere. So optical fiber is the device which is used for this purpose. The guidance of light beam by total internal reflection was demonstrated in a water jet in 1842 by Colladon. And fiber uses exactly the same technology. That means the core is high index, which is surrounded by lower index. And hence at the interface, which is here, you get a total interreflection. Exactly much the way you have water surrounded by air and you have total interreflection and the light follows the path of water. Similarly here, light will follow the path of the optical fiber. This is the decorative fountains which were used for more than 100 years now for using the same kind of, let's say, principle of total interreflection within water surrounded by air. So optical fibers were used since the mid 20th century as optical elements to transmit light and images for applications in endoscopy. Endoscopy, as you know, that you want to see inside the body and what is happening. So you want to see the images from inside the body. So these endoscopes were used. One very famous Indian, Narendran Singh Kapani, NS Kapani, was at the core of the development of these endoscopes in the 50s. He did his PhD at Imperial College with H.H. Hopkins, and they together developed a lot of new technology for glass, particularly coated glass rod. That means you have a glass rod. Earlier glass rods were used in air and they were lossy and scattering and so on. So he invented that if the glass can be coated with another glass of lower index, then it will serve the purpose. So it came, the cladded fiber concept or a cladded rod concept was given by Kapani. And he also coined the word fiber optics. And he wrote the first book on fiber optics ever in the world. In 1965-67, he wrote this. So glass fibers and communication medium were examined by the communication engineers. The typical loss in glass fibers at that time was 100 to 200 dBs per kilometers. 3 dB means after a kilometer, half the light will remain, half intensity. 10 dB means 1/10 will remain. 100 dB means 1 in 10 to the power 10 will remain. So it's hardly any light will remain actually. So most technical opinion of communication engineers deemed glass-clad fibers excellent for medical imaging, but not for communication over long distances because of these losses. And they rejected, and they started looking at other technologies and other means. which today, if you look at those papers, sound very weird actually. That how could people even think of using those for long terms? But fortunately, a small team at Standard Telecommunication Labs in the UK did not dismiss the potential of glass completely. And Charles Couch, who was one of the engineers in this particular lab, he collected samples from fibers and carefully researched the properties of bulk glass. And he showed that the high loss in optical fibers was due to impurities and not because of the silica itself. Silica is the main component. So in 1965, he wrote the paper, which was a part of one of the thesis of one of his students, Hakam. And so in 2009, he was given Nobel Prize for this groundbreaking achievement concerning transmission of light in fibers for optical communication. So what he showed, what that if you can carefully make the fiber devoid of impurities, the losses would be much less. And in fact, he gave in this particular paper, he gave the entire prescribed basic design, what should be the diameter of the fiber, or how it should be made, and all the details were given in this particular, let's say blueprint was given in this particular paper. But not many people bought that idea at that time, and communication engineers did not sort of listen to him carefully. But one team at Corning Glass Works, led by Maurer, they said, let us try to make fiber now in such a way that the glass is low loss. And they made this in 1970. And the first low loss fiber was made with 17 dB per kilometer loss in 1970. So today, this year is also 50 years of optical fiber, not only 60 years of lasers, but also 50 years of optical fiber. This also happened in sometime in the May 1970. And what was the breakthrough that they actually thought of? So what was happening is Kapani and others were making fibers starting with glass. They would buy glass from Corning Glass or from Short Glass or whatever, and then melt that fiber in a crucible with a hole, and that will outflow would be a small glass stream, molten stream, which will solidify, and that is how the fiber was made. So when you start with the process like this, the glass already has impurity, and hence when you convert glass to fiber, it doesn't improve anything. So what this Corning Glass team thought, that we have to start with making of glass itself, and that is how they started with the ingredients for the glass. That means, what is glass? It's silicon dioxide plus some modifiers, germanium dioxide or bromium and other things, or other chemicals. So what they did, they started with liquid form of silicon tetrachloride, etc., and through oxygen, they bubbled through the oxygen through these and burned that oxygen, that fume, with at a high temperature, which formed a soot like the kajal, inside the tube or outside the tube, but deposited layer by layer, and that is how this lathe was used. This lathe was used for the heating, and these fumes were put through which had all these chemicals and oxygen, and silicon dioxide was actually made in situ, and this made the possibility of very low loss fibers. So today, optical fibers, which are extremely thin, flexible, and transparent, made of glass or plastic, these are hair-like fibers transmit light signals from one end to the other end and over long distances when joined end to end. Most commonly used in telecommunications, the use of light in fiber optics has revolutionized the way humans interact in 21st century, that we know this. Unlike wire cables, optical fibers permit transmission over long distances. Earlier with microwave and so on, you had to have a repeater every few kilometers. Now people are going tens of 100 kilometers, and no repeater is required. Fibers are also used because signals travel through them with less loss than any metal wire, and they are also unaffected by electromagnetic interference, any other presence of any other electromagnetic wave does not interfere with that. So today, if you see the fibers, the typical wavelength used is 1550 nanometers, and the losses are 0.25 dB kilometer. That means after 40 kilometers, you still have 1% power. That means you start with 1 milliwatt at one end. After 40 kilometers, you will still have 10 microwatts, which is good enough for detection. So that is how the fiber has revolutionized the communication. This is a typical fiber, as you can see, the size, relative size. The structure is typically like this. You have a core of high index, you have a cladding of low index, which is fairly thick. The core is typically 10 micron in diameter. The cladding, this is called, is glass, is 125 micron in diameter. And then, of course, glass is fragile and so it should be protected with some plastic or polymer jacket. The advantage of this high capacity, because as I said, 10 to the 6 times capacity increase in one go when the technology changed. That led for all the communication engineers to start with digital communication itself. Nobody thought of doing optical communication with analog because there's a digital requires a little more bandwidth, but here there was no limit of bandwidth. There was no limit on the bandwidth. So initially, from the very beginning, it became a digital, and that was a boon because this digital communication, which was binary communication, 0 1s you are sending, became completely in line with the computer technology. And that is how internet became very, very easy. You have a computer, all the technology is actually digital. So that is how it is made. So basically you take a signal, analog signal, voice signal or any other signal, make into pulse trains. So pulse is 0, no pulse is 1, no pulse is 0. So send a stream of 0 1s. At the other end, after some time, because of the defects or let's say properties of light, this becomes slightly broader, but that doesn't matter as long as you can still see that where the pulse is and where the pulse is not there. If you can recognize that well, you can still make the signal completely exactly the same what you had started. So the efficacy of the signal, or let's say fidelity of the signal, was extremely high. And hence today, that is why it doesn't matter whether you're sitting in across the room or sitting in another town or sitting in another continent, the voice quality or the signal quality is the same because it's all digital. So if you look at the capacity, these are some old slides, but things have changed slightly. But if you see, a telephone channel requires 64 kbps because 4000K is the frequency used for data rate, and each sample is coded with 8 times, so that becomes 64 kbps. So if you, and these are other things. So if you look at one single fiber, which has typically 40 gigabits per second kind of capacity for 40 kilometers without any repeater, that means it can actually transmit 600,000 voice channels to 40 kilometers without any repeater. It's a tremendous capacity as compared to what is there. So that is why today, when you call somebody, you get a busy tone only when that person is busy. It never happens that one of the exchanges is busy or something like that, which used to happen long back. Either the local exchange is busy or the international exchange is busy or something is busy, and so you are not able to go through. But in this, there is no problem. So you are actually always it is one-to-one communication. So this is a typical system. You have several wavelengths. This is called wavelength division multiplexing. You can send several wavelengths through a particular multiplexer to a single fiber. So each wavelength is like a single channel. So each wavelength is, let us say, carrying 40 gigabits. If you have 100 wavelengths going into it, that becomes 4,000 gigabits, which is a huge capacity actually. And then you have, this is the fiber link, you have amplifiers, because there is still loss, which is called 0.25 dB. And if you want to reduce that further, if you want to go to several hundred kilometers, you would like to reduce that loss. boost up the signal. So you have optical amplifiers, and then you have take out and add in kind of channels, and then you demultiplex. So this kind of channel, if you see, you can actually have a capacity of 1 terabit, in fact, even more these days. So if you look at the internet usage because of this optical fiber over the years since 90s, today, as I said earlier, 62% of the population is using internet. So 4.8 billion internet connections are there. And today, in 93, only 1% of the information was data. Today, 99% probably is all data. Okay. This was the as we use the word, these are disruptive technology. The with the electrical signal, this is how the capacity was increasing with various technologies. What with optical technologies, the slope completely changed. So it was completely disruptive technology. It's completely changed the slope of the bandwidth evolution. But even today, as you know, as we are doing this Zoom or video conferencing, we have a problem of signal. So we get into the bandwidth problems, and it's still there's a demand for higher and higher bandwidth, and hence ways to increase bandwidth are still vigorously being pursued. So one of the ways was the WDM, which changed with the same fiber, you could send several wavelengths. Then came the optical amplifier, which could amplify all of them together. That was a great thing. But now people are trying to use other properties of light, like wavelength was one, to multiplex signals. So polarization multiplexing or angular momentum multiplexing are being considered. Mode or space division multiplexing is another way which is being considered. I'll just take a slide on mode and space division multiplexing. What is happening is that most of the communication that is happening today, long distance communication, is through single mode fiber. A fiber in which only one mode propagates. Mode is the way the electric field configures to propagate. So there's only one way of doing that in a single mode fiber. But if you have a slightly different fiber, which is called few mode fiber, you can have, let's say, 4 modes in the same fiber. When you can propagate 4 modes, each mode is independent of the other because they are orthogonal to each other. So that would mean actually they become 4 channels. And hence the capacity becomes 4 times. So what is done is that you have 4 single mode fibers, which are bringing, each is bringing a different channel. And then you put all these data of 4 into one few mode fiber. And then that carries long distance, and on the other side, you will separate them. So this is the kind of thing which is called space division or a mode division multiplexing. For this, you need a device which will combine or, yeah. Hello. Yeah. So you have to combine or decombine the signal from single mode to multi-mode. So for this, there's a device called photonic lantern. So you have a multi-mode fiber, you have several single mode fibers. So you taper down, it becomes this, taper up, it becomes that. So single mode to multi-mode and multi-mode to single mode. And these are very long devices. So modeling these devices is a difficult thing because you have to propagate several centimeters the light. Usually light propagation is done in fraction of a micron, and so it becomes very, very long, several days of propagation. So we have recently done some new analysis and showed how light can be propagated through this in a faster way. And this is how it happens. This is one of the single mode fibers, and then it sort of evolves, and it evolves into one of the modes of the multi-mode fiber. This is how this particular device works. You can have a 6 core. So each core corresponds to one mode. So this core corresponds to this mode, this corresponds to another mode. So depending on which fiber you excite, a different mode is generated in the multi-mode end, and that is how the orthogonal thing goes. And so you can have actually several modes. And so this kind of device is extremely important. And its design and optimization work is still going on. And we are also looking into the how this can be done. There are few developments that have taken place because of the fiber itself. I was talking about the amplifiers. So these erbium doped fiber amplifiers, that means you take a fiber in the core, you dope with some molecules of erbium, and that becomes now an amplifier. And this, the beauty of this amplifier is that it is completely transparent to the wavelength in the window of the communication, and also completely transparent to the bit rate. So it just takes the input signal and just amplifies it without changing anything else. And so this is a completely passive kind of a device as far as the signal is concerned. But of course, it's a very active device. It's a laser in some sense, or it's an optical amplifier. So this is something which has complete. I mean, without this, things would have been very difficult, because then you have to take the signal, amplify electronically, and input into the optical fiber. Would have been very, very difficult thing. But in 1987, this kind of thing was developed, and since then this has become part and parcel of the optical communication. The same thing when you put two mirrors on the amplifier, you get a laser. So people have now made what is called a fiber laser. So you take the fiber, you dope it with erbium or some other rare earth material, depending on which wavelength you want, and you can actually make a fiber. The advantage of fiber laser is that it's a very lightweight thing, because all the power, everything can be away, and it is flexible. So it can move very fast. So in manufacturing, in cutting, welding, it is extremely useful these days. In fact, most of the auto manufacturing, and in fact your mobile, the sleekness of the mobile that you see that you have in your hand is because of this kind of laser, which can be used for manufacturing these. Then you also have a supercontinuum source. Because the light is so intense, you can have a very small pulse of a very high intensity. So cascading of entire nonlinear effects can happen, and you get a very broad optical spectral signal, almost white light, which is like coherent light, white coherent light, which is extremely useful in many applications. So you have a pulse which has a very narrow width, but after a certain distance, you get a spectrum of this time. So you see from 0.4 to 1.6, it's a huge white and super white light, actually beyond white light. You can get this kind of source, and this is extremely useful in several imaging devices. So photonics technology is an enabling technology. What it means, what is the meaning of this word? That means it's a critical technology for the entire operation, but it's a small part of that. It's like heart of the whole body. Heart stops, the body stops. But heart itself is a very small part. But the entire thing depends on this. And that is how the enabling to it enables the entire application, but it's not the entire application by itself. That's why it has to depend on electrical engineering or mechanical engineering or chemical engineering. It has to sort of combine with something else. So in defense applications, you have vision devices, as I said, detection, annihilation devices. For space applications, you have cameras and sensors. You can send any number of satellites. Unless you have good cameras and sensors on them, they are of no use. Industrial use for cutting, sensing, control, lighting. For energy, solar cells and LED lighting. For science and research, microscopy beyond diffraction, molecular manipulation. These days, you can actually have, this was also Nobel Prize in 2018, that you can have a small molecule or a small ball, very light ball, and you can laser and you can manipulate that particular thing the way you like. The movement can be it can be trapped and then moved. High power pulse laser of extreme intensity. This is another field which is coming up. Now the pulses have become so narrow that they are not only femtoseconds but also attosecond. That means the duration of the pulse is 10 to the minus 18 seconds. And these can be extremely high intensity, extremely. So the intensity that is falling on a material is of that type that actually can dislodge the electron from its orbit. And hence you can actually make an accelerator. And so a lot of things are happening these days. This is called extreme light. This area is called extreme light. That means you are extreme in the sense intensity is very high and the pulse is very, very narrow. And that is how this can use for creating a new kind of radiation like terahertz radiation and so on. It can also use for accelerating particles. So actually people are going to now have tabletop particle accelerators instead of huge buildings which are used for accelerating particles. So optics and photonics enabling technology can offer innovative solutions to many problems in the society, and it is doing so. It is generally integrated as a key element with other technologies I said earlier to provide solutions. And hence it is important that the engineers know at least basic properties of optics so that only then they will be able to even think of using it for their application or solution. A higher level of awareness about light and its properties is needed to aid this. Unless you know about the properties, you will not be able to use it. What is the scene in India? We have a very small R&D community. General awareness is quite poor. In education, the content is poor. Optics is not a subject at MSc level except in few institutions like IITs. Engineering curriculum is almost devoid of photonics content. Whereas I always say that there should be at least one course for all engineers. Hardly any training at the technician level. To get a technical person who is trained in optics, handle optics is nearly impossible. So this needs to change. This needs to change. That's the message that I want to give. Because if that doesn't happen, then we will let this revolution also pass by our country as many other revolutions have passed by. Thank you.
Dr. Ritu Sharma. Dr. Ritu, unmute yourself.
Dr. Ritu, please take over.
Thank you, sir.
Yeah. So if there are any questions or anything? Yeah.
As Albert Einstein put it that the important thing is to never stop questioning.
Yeah.
Now I request Professor Sanjeev Goyal to open question and answer session. You are invited to by raising your hands to ask the questions. You can type in chat box.
Thank you, Dr. Ritu. Am I audible?
Yes, sir, you are audible.
Yeah.
Okay, thank you. Thank you very much, sir, for very informative lecture. It was a very excellent presentation. We all knew photonics in detail. Now, there may be a few questions, but I'm seeing that there's no question in the chat box because the lecture was so very well covered by you. So people are not interested to ask question. There's one question, it is just different type of question by Dr. Manoj Mangal. He says that there are a number of theoretical research papers, but applicability is very rare. Why it is so? The theoretical research papers are more, but applicability is very less.
Is he talking about the Indian scenario or is it about international? Internationally, it is not correct. There are so many applications which are actually doing only technological. In fact, only in India that we have some theory work, but there are also good experimental work. But of course, we are not at the high level of technology because it requires a lot of not only manpower, a lot of if you once we were doing this photonics conference that we do. I tried to count how many people working in photonics in the country. I mean, there were only a few hundred at the senior level. So the point is, we have to have a large community, and then a lot of investment is required because optics is investment intensive. But it's not correct that it's all theory that we are doing. I'm doing most of the theory. That you can blame me. But I have my colleagues who are doing a lot of technology. There are a lot of applications working in biomedical engineering, kind of biomedical imaging kind of applications, and many other applications. So there are a lot of experimental work is also going on.
Right, sir.
But it is not at the level it should be. Yeah.
Okay. Now I invite Dr. Pavan Kumar. to ask a question.
Yeah.
Dr. Pavan Kumar.
Good afternoon, sir.
Good afternoon.
Sir, actually, my question is that a lot of people are working on the terahertz communication
Right.
and terahertz frequency. Sir, which is better for terahertz communication or at optical frequency communication?
No. If it is a question of only communication,
Yes,
then
sir.
of course optical is established because the frequency is much higher.
Yeah.
Terahertz is only slightly larger than microwave. But advantage of terahertz is that it can penetrate in several things like body and other. So imaging applications are very important. So terahertz not so much for communication.
But sir,
But
yes,
just
yes.
one minute. Yeah. But the problem is with the optical that it cannot be wireless.
Yeah.
But terahertz can be wireless. So
Yes,
for
sir.
short distance, when local area type, right now people are using microwave, but in 5G they are moving to a higher frequency. Okay, from 4G to 5G, when they are going to higher. You will see that the antenna all become very small. But that means wavelength has become small. The frequency will be high in 5G technology. And if you go further, then the terahertz will come. So if the terahertz technology is developed, then you see what happens is the higher frequency is required for more data communication, right? So fiber, for the backbone, the fiber will remain. But the question is from tower to your mobile. You are right now limited because of microwave. If that frequency goes up, so for that the terahertz will come for the local area wireless connectivity. Okay, but
Okay,
not
thank
for
you.
the long haul city to city. That will remain.
Yes.
Yeah.
Okay, thank you, sir. So another question is that like as we are doing also did work on the optical fiber. Is sir graphene coated optical fiber is good for terahertz wave guiding?
That I don't know really exactly. I'm not working in terahertz.
Okay.
But you have to create for terahertz optical. If you want to use fiber for terahertz, you have to create this high index and low index environment. The core has to be high index.
Yes, sir.
And the cladding has to be lower index. So for that purpose, maybe people are using.
Okay. Okay. Thank you, sir.
No.
Thank you, sir. Thank you, sir. Is there any other question from anybody? Please raise hand.
Sir, you can ask your question.
Yeah, good afternoon to all the members.
Yeah.
Good afternoon, sir.
Yes, sir. So I would like to ask the question related to optics. Optics is only the feeling, we can feel. But sir, in class 12th standard, we are only taught about the theoretical. अगर ऑब्जेक्ट फोकस पे बनना है तो इमेज इन्फिनिटी पे बनेगी. ये तो सिर्फ थ्योरेटिकल पढ़ाया जाता है, हम लोगों को फील नहीं आता. तो सर ऐसा क्या कर सकते हैं कि जिससे बच्चों को पता तो चले कि ये इमेज कहाँ पे बन रही है. जैसे कुछ जगह बताते हैं कि बियॉन्ड 2F बन रही है, तो ये तो सर थ्योरेटिकल हो गया. सिर्फ हम लोग बुक में डायग्राम बना करके कैसे
लैब में एक्सपेरिमेंट नहीं करते हैं.
नो सर, लैब में एक्सपेरिमेंट नहीं कराए गए थे सर हमारे यहाँ.
अब तो लैब में एक्सपेरिमेंट करे बिना फील कैसे आएगा. वो लैब में एक्सपेरिमेंट आजकल क्या 12th में होता नहीं एक्सपेरिमेंट.
नो सर यूपी बोर्ड में बहुत कम जगह होता है सर.
उसी वजह से फील नहीं है.
So no, basically this does not require very expensive equipment. I mean, just a small table or a bench kind of a thing, and you just one lens that can very easily show this F to F, and this is very, very simple to show.
Okay, thank you, sir.
सर लक्ष्मी प्रसाद सर को भी एक क्वेश्चन पूछना है. उनको अनम्यूट कर दे कोई.
अनम्यूट कराइए.
सर आपको अनम्यूट करना पड़ेगा.
हाँ, अब हो गया.
Is that okay?
Yes, sir. Very good.
Acha, that's two things I have to place before you.
Sir.
One is that earlier we had communication on metal wires.
Right.
Then we have changed to this optical wire. And now, after all, the science is extending the boundaries of the research work. What is it that you are seeing after 50 years? Whether this optical wire will continue or there will be something else?
See, as far as, as the frequencies will go up, you will have to have some medium. you cannot send light in open air. That is for sure. So you will require this, you know, the what kind of fiber we use is changing. Right now we have a solid core fiber, and then you have a solid cladding fiber, in which you have some loss because there will be some scattering, which is 0.25 dB or 0.2 dB per kilometer. If you want to avoid that, then people are making which are called hollow core fibers, which are based on photonic band gap principles and so on. They have not yet come to a level where you have very long distance fibers. For short distance, short length fibers, they have been made for special applications. But if a technology comes through, maybe later you will have a fibers which are hollow core fibers. Then the loss would be even much less than this. So that could be one direction.
Now, second thing is, only yesterday, our Prime Minister, Honorable Prime Minister, he has dedicated this 2,000 kilometers optical fiber lines connecting India, Andaman.
Yeah.
And I think your point is well taken that when such a massive use of optical fiber is going to be made, where are the engineers and where are the technicians to handle it?
Yeah.
So I think you must be there in various boards of the universities. This kind of proposal has to go from somewhere, that this optical fiber, photonics, etc., should be made as a important subject of teaching, both in engineering as well as in the science part of it.
Yeah.
This is my suggestion to you. And the third thing is an appeal.
Yeah.
My RKGIT has a very strong group in physics. Dr. Sanjeev is here, Dr. Pavan Kumar is there, Katoch is there, large number of people who are working on this physics side of it, and they are very dedicated and sincere fellows. Now, how do I connect these persons to you in IIT? What is the mechanism?
No, you see, science works with all kind of collaborations and so on. So, you know, one way is to, first is to sort of have a familiarity, have some interaction and so on. And if things go to a certain level, then there could be a formal collaboration and so on. But otherwise, you know, if we start interacting, if you want to, you know, visit us or you want me to visit you, I mean, that can be done. I mean, that's not an issue at all. I mean, now I'm formally retired in any case. I'm emeritus professor. So I'll have more time probably. But then we can have, you know, first informal, and then if it grows to a certain level, if there's interest, then it can be formalized. Because if you formalize the beginning, it may not work at all. So then there can be several ways of looking at it. Yeah.
Okay, that's up. And lastly, I must put my hearty welcome. Of course, it is towards the end of the seminar. And thank you very much for such an illuminating lecture. Thank you very much, Dr. Anurag.
Okay, my pleasure, sir.
Okay. Thank you, sir. Thank you very much. Is there any other question?
And sir, from my side, the slides were beautiful, beautifully made, very clear, very legible, and beautifully made slides.
If there is no further question.
Dr. Sanjeev, I have a question.
Okay, okay, sir.
Sir, मेरा question है. We are talking about these multiplex theaters.
Multiplexers.
Yes, multiplex theaters, cinema halls.
Okay, you have multiplex theaters. Okay.
Yes, is it related to the science or is it just a name is given like that, sir?
No. See,
what is the technology in that, sir?
No. Multiplex. No. There is not. Multiplex means putting several things together. Okay. Sure. So now earlier you in cinema halls you used to have one screen. Now they have 3 or 4 screens in small size rooms. So that is how they call multiplex. I mean, there is nothing more than that.
There is nothing to do with this
No. Here multiplexing means you are putting several wavelengths, technologically putting them all into one particular fiber. So that is called multiplexing. So multiplexing is basically putting several things together in one basket or one particular unit.
That's all. There is nothing to do with the science.
No, nothing to do with this.
Fine, sir. Sir, मेरा एक second question है. Sir, about say 1 decade back or 2 decade backs, there was a lot of research was going on. This electrical wire, along with the electrical wire, or in the same wire, the internet wire also can be. The internet can also be passed.
Yes.
So what is the? Can you throw some light on that, sir?
No, yeah. So a lot of things were being done at that time, and now it is also being used. So what they do is they can make actually the wire the conductor is made hollower inside the core. You put the fiber. You see, the advantage of the fiber is that the high voltage or high current doesn't affect it, right?
Sure.
So it can be put together and it can be used. So some applications were there, but the only problem comes when the fiber has to jump on a pole, because on a pole you have now a different, the wire disconnects and it connects to something else and so on. So there were some difficulties, but I think those things have been sort of taken care of, and people are at some places it is being used.
Sure.
Thank you,
sir.
Yeah.
If there is no further question, then I ask Dr. Ritu to take over. Dr. Ritu, please. I think there is no further question.
Dr. Ritu, unmute yourself.
Awesome, a very interactive and informative session it is. Thanks, Professor Sanjeev Goyal and the participants who actively participated in the session. Now I invite Professor Shalini Gupta to give a vote of thanks.
Shalini, unmute kar lo.
Over to you, Professor Shalini. I think there is a technical issue.
Shalini ma'am, check your sound. No, you're not audible. You're not audible.
Professor Shalini Gupta, you are not audible.
No, you're not audible. Just check your mic.
As they are technical errors.
That is a problem with this. Technical glitch is always there, somewhere or the other.
Yes, ma'am.
Where there is technology, there will be glitch.
Yeah. Yes, Shalini.
Not
नहीं
audible.
आ रही आवाज. कोई बात.
Okay, I continue then. I express the vote of thanks.
Shalini, we can't hear you. Let's just speak.
Dr. Poonam, you take the privilege.
No, sir. Sanjeev Goyal will take the privilege.
Achha.
Okay,
Because
sir.
there is a problem from Dr. Shalini's side.
Yeah, she's not audible at all.
Yes.
And we checked, when we checked, it was okay.
Okay, very sorry, Dr. Shalini. You are not at all audible. Right.
No problem. Okay. Thank you, Professor Anurag, sir, for enlightening us with the remarkable knowledge sharing on photonics revolution. We hope that the faculty members, the students, and the people from corporate world, whosoever attended this lecture must have been benefited in many ways. It has been a very informative and interactive session for we all. We express our gratitude to Professor Anurag Sharma, sir, for giving us his valuable time. We hope he will continue in future too to kindle our thought process. We are thankful to all the respective participants for their keen interest and involvement throughout the lecture. Our thanks are to our organizing team and technical team with whose support this international webinar series is continuing beautifully. Thanks to colleagues for coverage in press and media. We express our heartfelt thanks to RKGIT Vice Chairman Sri Akshat Goyal sir, Director Dr. D.R. Somasekar sir, Group Director R&D Dr. Lakshman Prasad sir, Executive Director sir, Director Academic DSW Professor Shri H.G. Gak sir, and Dean Second Shift Dr. Puneet Chand Srivastava for their inconsistent support always. Thank you to all once again. Thank you very much.
Now everybody switch on your video. We can take a picture snapshot.
Thank you, sir. Thank you very much.
Itu ma'am, ask everybody to switch on the video and somebody can take the snap.
Please
All
switch
the
on your
organizing
video.
team and department.
Please switch on your video for a snapshot.
Jatin sir, you too.
All
Yes.
the participants, please switch on your video.
And when it is done,
All the
please let
members
us
of
know.
organizing committee, please switch on your video. I request Dr. Neena and Dr. Garima to take a snapshot.
Yeah, but I think it must have been done because
Sit down.
I think it is done.
it is done. I think it is done.
Sir, thank you, sir. Thank you. Namaskar, sir.
Okay, namaskar. Thank you.
Thank you very much, sir.
My pleasure. Okay.
Thank you, sir. Thank you so much.
I would like to thank all the wonderful people for taking time out of your busy personal and professional schedules. Good morning, everyone.
Okay. Bye.
And happy Janmashtami to everyone.
And
Happy Janmashtami, sir.
ma'am, voice is not audible actually. Like this.
Voice. Is it audible now?
Yes, yes, very much audible.
Very happy Janmashtami to everyone present. And let's celebrate Janmashtami in the evening. Thank you very much, sir, and thank you all.
Bye.
Bye, bye,
Thank you. Thank you.
And all the participants can fill the feedback form and then they can leave. So, technical team, हम लोग कितनी देर तक अभी open रहेंगे for feedback?
The feedback is available. Participants can fill.
Okay, so maybe 10-15 minutes more and then we can end the session.
Yes.
As you say, we'll end the session.
You can just check how many have filled the feedback and then we can accordingly end the session. Maybe 10-15 minutes people will take and then we can end the session. People are already leaving. I think they have done. थोड़ी देर में हो जाएगा. 10-15 मिनट में I think it will be over.
Should I end the session?